Aphaenogaster cockerelli by Hightower. Aphaenogaster cockerelli is a species of ant that lives in queen-right colonies, typically underground in tunnels that have been burrowed out by worker ants. From previous experimentation, it has been proven that Aphaenogaster cockerelli and a myriad of other insects use hydrocarbon profiles as cues for discerning a number of things, such as mate selection, determining potential threats, and identifying variances within the colony. This led me to hypothesize that in the specific queen-right colonies, worker ants, using the information from hydrocarbon profiles, become more protective of eggs laid by the queen than they are of eggs laid by other workers. This hypothesis was confirmed by Adrian A. Smith and others in 2008 when they observed the success of queen eggs exceeded that of worker-laid eggs. It was also observed that if the workers shifted their attention to the worker-laid eggs, that the success of those would be far less than if they prioritized the queen eggs. Though this cannot be directly observed, queen-right colonies operate in a manner of a pseudo-hierarchy, where the workers work, defend, forage, hunt, and maintain the nest, while the queen is the centerfold of the success of the nest and reproduction. Although a queen-right colony can be broken into two general groups, queen and workers, variations are present in the working sector. Work allocation is something that is constantly changing within the colony. It would be unlikely for a colony to allot all of its resources for foraging, nest protection, nest maintenance, or other various tasks. Based on this inference, I hypothesize that work allocation is distributed evenly amongst ants, where all levels of work are distributed evenly and proportionately. As you can see here, the ants scurry around the leaves placed near the mouth of their hole. Nearly 1 to 3 foraging ants come and observe the leaves that have been placed there. This hypothesis was not fully supported, as N.J. Sanders and D.M. Gordon observed in 2002 that ant work allocation is based more on resource availability. There are also hydrocarbon complexes on the exteriors of the ants that are used as cues to discern variations in workers. This leads to my next hypothesis that the ants have a more herbivorous diet. This is largely due in part due to the availability of resources as well as the degree of difficulty of attaining such resources. Over time, their fitness has increased in attaining such resources. This hypothesis was partially proven by Adam Kay in 2004 when he observed the diet preferences of many insect species. He concluded that ants tend to choose an herbivorous over carnivorous diet, but when presented with the opportunity, the ants will elect an omnivorous diet to maximize on the nutritional advantages provided in both food groups. The ease of extracting herbivorous resources is clearly more advantageous to ants, as the risk is minimal and quantities extracted are often greater. As you can see here, ants within this colony are working together to perform their various tasks to support the hive. Unlike many other species, ants have a way of identifying members of their colony, different colonies, and enemies. This led me to believe that ants use chemoreceptors to discern between all communal encounters. M.J. Green and D.M. Gordon's work in 2007 further proves my hypothesis, showing that ants recognize specific hydrocarbon cues relative to their colony and treat others as threats or non-threatening factors.